Okay, our next topic is structural equations. Um, so let's say that somebody comes and gives you a density for these three random variables, x, y, and z, and they say this is the density formula. And you can write it as a formula. What this, again, to kind of refresh our ideas of functions and things like that. Functionally, you can think of this as a table where you have x, y, and z, right? And you imagine what this is telling you is that if I give you a value, let's say x is 1, y is 2, and z is 3, and I want to know what is f, x, y, z, the way that I get this value is by just plugging these numbers into this formula up here, right? And then that will give me the value that should go in this table. Now, in this case, some of these are continuous random variables, so actually this table does not have a finite number of rows, right? So it doesn't totally make sense to think of it this way. But hopefully this kind of helps you understand when I write a formula here, it's just a way of getting another column. It's like a mutate, right? So these things are being mutated using this formula into the value that goes here. Okay, so I can give you a joint density or a conditional density or whatever, not as a table, but as an actual function like this, right? And when I have that, I can compute probabilities and things like that, and everything's cool. Now, I don't know about you, but I see this and it makes me want to die. There's a lot going on, and none of it really makes that much sense. So this is actually not the way that most often you're going to see joint distributions expressed, because it's kind of hard to read. But you may, if you think very carefully and closely about it, you may actually notice that some of these things are densities in their own right, and the way that I've written them. And there's no way you could see this right now, so don't think you're dumb if you don't see this. I'm just telling you that actually these things are themselves densities. So maybe you can see this if you remember the last lecture, we talked about the uniform distribution, which has for a continuous value, is the density function is, in the previous section here, in this lecture, we talked about the uniform distribution that has a density function which is 0 everywhere except for it goes up at 0 and then stays flat and then goes down at 1 and then is 0. And that's what this is. And so this is like the marginal density of a variable z that has a uniform distribution. Now over here, this you may recognize as the density function for a normal random variable. The only difference is that I don't have mu to be the fixed mean. I have z, right? And so, but if I condition on z, if I say z is some fixed number, so in the subpopulation where z is 2, right? Then this is exactly a distribution of a normal random variable y that has mean 2. So I'm going to write this as the conditional distribution of y given z. And similarly, this is actually a Bernoulli random variable that has it's like a coin flip, right? X could be either 1 or 0, and it takes x takes value 1 with probability equal to this kind of like scaled version of z. So z kind of tells you what the bias of the coin is. And again, it's really hard to see that by just looking at this formula. And so that's not actually the way people typically think about densities. People look at them, they factor them, or you may need. It's not even that these exist like this. It's like more often you're not even gonna get to the point where you write it all out in the first place, because the way that you're actually thinking about this is like this. So you imagine like z has a uniform distribution, and then x is a random variable where basically it's a coin flip, and then where I look at the value of z and I compute this this function, and this thing is a number between 0 and 1, which tells me the probability that my coin flip x is going to be 1 or 0. So based on the value of z, I compute x, and then based on also the value of z, y is a normal distribution where that has mean equal to z and standard deviation 1. So I don't know about you, but I think this is a lot nicer to read, and it also translates much more immediately to code. So we also talked about how to sample from a given distribution like uniform or Bernoulli or normal, and the code in this case, to sample from a joint distribution, very much mimics this kind of notation here. So this is called a like a structural equations notation, and what it tells you kind of exactly how to sample these random variables to get your joint distribution of interest. So here, if I wanted to get sample a population where the density of these, or to draw a sample from a population where in the population data set the joint distribution of x, y, and z is given by this crazy density, all I need to do is this. So first I pick z as a uniform random number, basically random number between 0 and 1, and then that's done for one person, right? I have their value z. Then the value of that person's x is going to be, I flip a coin with probability equal to, and then lastly, to get the value of y for this person, I plug in z to be the mean, and I sample from a normal distribution where that mean is z. And I just do that 100 times to get my sample. Okay. So let's try it out. So in a population of interest, let's say x has a standard normal distribution, and then y is going to be uniform between minus absolute value of x and x. So I want to first write this in structural equations, and then let's try to write the joint density as a function of x and y. In the real world, like you will probably never have to do this, is what I'm trying to say here, but I think it's good to think about it at least once. And then lastly, translate it to code, and then use sampling to approximate this conditional probability. So this here I'm asking you to kind of put together multiple ideas that we've learned about. So do try this yourself. Pause the video, try to parse what I said previously, and work this out. And if you're confused, that's okay, because I'm going to show you how I do it, and hopefully that clarifies certain things. And if you have questions, bring those to lab. But it's always worth trying to do it yourself. First things first, let's write this in structural equations. So step 1, x has a standard normal distribution. That is easy enough. The way that we write this is like this. So this little tilde guy, well, first we write the name of the random variable, x, tilde, and then the name of the distribution with any parameters that the distribution has in parentheses. So here this is what a statistician would understand to be a normal distribution with mean 0 and standard deviation 1, which we call the standard normal distribution. So that's x. Y is uniform random variable. So if it says standard uniform random variable, then this would be, you could write this as 0, 1, because these are different zeros. This is not mean and standard deviation. For uniform, the parameters are the minimum and the maximum. So this is a random number between 0 and 1, so means different things in different contexts, right? But here, that's not what we want. We don't want a standard uniform. We don't want a random number between 0 and 1. We want a random number between minus the magnitude of x and the magnitude of x. So it's like this. And then moreover, we should actually write, that's not the distribution of y, that's the distribution of y given x is a particular value. So this is our structural equations kind of notation for this joint distribution. Next thing is to write the joint density as a function of these two things. So let's just write from this, it's actually quite easier to write the marginal distribution of x and the conditional distribution of y given x. So let's do that. So this one, we know the density of the standard normal is what? 1 over 2 pi. Again, this is just a normalizing constant. The important part is the e to the minus, it should be x minus mu over standard deviation squared, but here it's standard normal, so it's just going to be x squared. Okay, so that's the density of this, the marginal density of this. This conditional density for a given little x fixed is the function that's 0 everywhere, except for it takes the value 1 between these, wherever it's between these two values. So let's write this actually first a more intuitive way, and then I'll show you what the kind of usual notation is. So I'll say this takes the value 0 if little y, the density for this takes the value 0 if little y is bigger than the absolute value of x, or little y is less than the negative absolute value of x. Okay. And sorry, this should be a little x. And I can maybe write that a little more neatly. So I'll just say y is bigger in magnitude than x is. Then the density is 0. There's no chance. And I'll say it's 1 if that's not the case, right? Otherwise. And now this is actually not quite right, because I'll show you what this kind of plot looks like here. So if this is minus x, here's 0, and here's the absolute value of x. This function looks like 0 here, and then it goes up to 1, and then 0, right? So that's what this looks like. The problem is that what's the area under the curve here? The area under the curve is the height times the length, right? So it's 1 times, this length is the absolute value of x, that's the absolute value, so this is 2 times the absolute value of x, which I need this to be equal to 1, which is not going to be. So in fact, the height of this function can't be 1. It has to be, this height, whatever this height is, has to be exactly equal to, let's put this height here instead. So height times this. This has to hold. So that gives us that the height actually has to be 1 over 2 times the absolute value of x. So that's what this value has to be here. 1 over 2 absolute value of x. This is new to you. This is complicated, but if this is direct, if you've been working with uniform distributions and you know how it's parametrized, you see this is just the density of a uniform distribution with min and max equal to this and that. So I had to go through this explanation because I'm trying to not show you things that are unfamiliar to you, but this is very, very direct. If you know what you're doing, if you go on Wikipedia and look up the density, you can get this directly, or ChatGPT. You don't have to kind of do this geometry and whatnot. Okay, so another way I could write that kind of in a different notation is I'm going to use the symbol 1 to denote a function that takes the value 1 on a particular region, whatever this region is, and then 0 everywhere else. And I'm going to denote what region it takes the value 1 on by putting it as a subscript. So I'll put minus x to x. And maybe these should be little x's again. Minus. And then what is the input to this function? It's the value of y. Okay, so this is the conditional density, or sorry, this marginal density, and this thing here is this conditional density. So to get the joint density from the factorization of density, I know I can just multiply those two things together. So the joint density is just this thing times that thing. And for any values of x and y, I can plug those numbers in, and that will give me the value of the joint density at x and y. That's kind of a lot. I'm really just trying to kind of to show you the mechanics of this. It's not really something that you should have to do. I'm just trying to deepen your understanding of densities and how they're related, and how you can write a joint density not by literally getting the functions and multiplying them together or whatever, but by just saying, hey, this thing has this distribution, and the conditional distribution of this other thing is this thing. And that actually gives you the whole joint distribution because of the factorization. Okay, so the last thing is translate this to code, and let's use sampling to approximate this particular probability. So let's do that. So Well, we want x to be normal, and then we want y standard normal, y given x to be uniform like this. Okay, so how do we get that to happen? So if we want to draw, let's just sample x. We know we can do, let's do this one by one. So we can just say x is our norm, and then however many people we want. So let's say that, let's just try to draw 100 people. Okay, done. So now how do we get y? So y, we know our unif is the uniform distribution. And here you have to put in the min and the max. So instead of putting min 0, max 1, or min 5 to 6 or something like that, I can just put in the value of x that I got. Or in this case, minus the absolute value of x, absolute value of x. And actually, let me show you with n equals 1 just so you can see. So here, this is the value of x that I got. Okay, cool. And now the y value that I get here, oh, I need to say n, of course. Sorry. The y value that I get here, why is it 1.03? Well, because x ended up being -2. So what I'm like -2 and a quarter. So when I'm drawing here, I'm saying give me a random number that's between -2 1/4 and +2 1/4. And so 1 is such a random number. But if I had run this thing again, right, I could get a different random number. But they're all going to be between, in absolute value, they're all going to be less than roughly 2 1/4. Because at this point, when I've gotten here, x is already fixed. Now, if I say n equals 2, then what I'm getting here is 2 values of x. Sorry, one sec. Make sure that worked. N equals 2. Okay, so now I'm getting 2 values of x. So for like 2 people in the population, I get one person's value of x, and I got the other person's value of x. And then when I run this line of code here, I get 2 values of y. The first value is going to be drawn from the uniform distribution where it's constrained to be between positive and negative 0.64. This value is drawn from a uniform distribution where it's constrained to be between positive and negative 0.21. So it's being done in a kind of a vectorized fashion. So you can see that here, right? This is a 0.5. This number could not be drawn from the uniform distribution with this as its min and max. It's too big. So it's the value of y that we get here is conditional on the value of x for that person that we got up there. So if I wanted to kind of wrap this up into generating a whole data set, it might be nice to do it like this. Well, you know what? Let me just put that around what I've already got. I just say, okay, drop that stuff in a data frame. Let's say -10. Well, I need to load tidyverse first, don't I? There we go. So this is my sample from the population. Where is the population data frame? There is no population data frame. It's implicit, right? It's the population data frame that is defined by the density, the joint density function that is the product of this marginal density and this conditional density. So this is the power of having densities and distributions, is that you don't have to have a population data set or even think about it. And I can summarize an entire population data set, that in theory, I mean, if this were referring to some, population in New Zealand that, in theory has like 5 million, 6 million people in it, I'm boiling it down to, just these two lines of code, or in the, if you want to write it mathematically, like two lines of mathematical notation. So it's really quite a powerful abstraction.